work on. Okay, so today we're doing 5.6 part 3. Okay, that's where your homework assignment is in Canvas. This homework assignment, 5.6 part 3, will be the only assignment that is tested on your next test. Okay, because your next test covers all of 5.6, parts 1, 2, and 3. But all of them are put together in this one lesson that we're doing today. So if you can do today's lesson, then you could do yesterday's and the day before. It's kind of putting it all in one picture, in one graph. And so since that's the case, your only homework problems that will be covered on your test come from this particular section. Okay, now when is that going to be? So today we're doing the lesson. Tomorrow is Friday. It'll be a work day. By tomorrow, I will publish all of the solutions for the homework assignment. So you can go through and read it, you can check it, you can make sure that your work looks good. In effect, I'm giving you all of the answers that might be on your test, right? I'm giving you my whole solution to the homework assignment so that you can do it, okay? So Friday's a work day. We're going to also call Monday a work day. I don't know whether that's a W. My life. It's fine. Monday is also going to be a work day. Tuesday is a short day because of EOC testing. And so Tuesday, I want your polished questions. You have any questions that you have over this section. And I want to nail those down. We're only going to have 30 minutes in class. I would ideally like to test on Monday, but I don't think that's swingable. I think it would be better if we had 2 days to work on this. And so we're going to test on Wednesday. And your test is going to only cover 5.6 part 3. And you'll see today that's plenty of test. Cool? Any questions on how that's going to look for you? Okay, like I said, this homework is already published in Canvas, and so that's kind of where we're headed, looking at that stuff. So for today, what does this look like? We're doing 5.6, part 3, and I would call this section curve sketching. Curve sketching. It's kind of what we call it in calculus, when we take all of the information that a function has to offer based on what we're looking at. And we kind of peel it apart and look at all of the different layers, and then we put it all on a graph. And we sketch the curve. We sketch the picture of what it looks like. Okay? So that's what we're going to do. The first thing that we're going to look at before we try our curve sketching business is I want to talk about the way the graph behaves on different asymptotes. Okay? So I wanted to show you this picture. I found it in your textbook. And this is a picture of the two different types of functions that we're talking about here. Everything that we've talked about in this unit falls into one of two categories. Either it's a reciprocal function or it's the reciprocal squared function. Okay. The difference in the two is that this one has 1 over x and this one has 1 over x squared. But what you can tell from the branches is that they behave differently, depending on whether it's x or x squared in the bottom, will determine the shape of the branches. Okay, so if the vertical asymptote has a multiplicity of 1, meaning that number in the denominator, the 0 that we're talking about in the denominator, only occurs one time, then our tails go in opposite directions on that asymptote. Okay, so they're going to look like this on that asymptote. Do y'all understand what I'm saying? Mm-hmm. Can you see that here? Now, if the multiplicity in the denominator on that 0 is 2, multiplicity of 2, then they're going to do what I call the volcano. And they're either both going to go up or they're both going to go down. But they're going to go the same direction on that particular asymptote. Okay, and you can tell that that's going to happen based on the multiplicity of the 0 in the denominator. Cool beans? Okay. So I took this picture as well. I'm always looking through the book trying to see what is it that I want to talk about. This is a picture from example 9 maybe. And I wanted to look and show you exactly what we're talking about here. No, this is not the picture that I wanted. Lies. Give me a sec. Cut. I'm not able to label the pictures when I take them, so I'm not ever sure exactly what's happening. Okay, this is better. This function right here, f of x equals x squared, or x plus 1 squared times x minus 3 times x plus 3 squared times x minus 2. Can y'all see this function right here? So based on the denominator, that's where I look for multiplicity. That's where I look for vertical asymptotes and for holes, right? Based on this denominator, what I see right here is that x plus 3 occurs twice, and that x minus 2 only occurs one time. And so at the vertical asymptote for x equals negative 3, what we see is the volcano action there. And at the vertical asymptote for x minus 2, what we see is opposite tails. One goes up and one goes down. Cool? Let's look a little bit closer here and see if we can make another general discovery. Look at the top. The top is the numerator. It doesn't determine where the vertical asymptotes are or where the holes are. But on the top, there is some very important information. On the top, I see that something happens at x equals 3. Can you look at the graph and find it? What is it? At 3, 0. What's the name for that thing? Where it crosses the x-axis? A 0, a root, an intercept. Okay? At x equals 3, there is an x-intercept. Do you find it? Okay? Find the other one. X equals negative 1. And I want you to notice what happens on the graph there. It bounces. Why does it bounce? Because that 0 has a multiplicity of 2. Okay, so this goes with exactly what we learned with our polynomial stuff. So we look at the numerator for the zeros, for the x-intercepts. We look at the denominator for the discontinuities, the asymptotes, the holes, that kind of thing. Are you following? Okay. All right, so before we start today, I wanted to get some rules down. We're going to look at two things that we want to do with these functions outside of what we've already done. We've already talked about their end behavior. We've already talked about the local behavior as far as the asymptotes or the holes are concerned. Today, I just want to define. So one thing that we might want to look at on a function is where it crosses the axes. Where it crosses the axes. So to find the y-intercept, how have we always found a y-intercept? F of x equals 0? Nope, that'll find me x-intercepts. F of 0. To find the y-intercept, plug in 0 for x and solve for y. We want to evaluate f of 0. We want to evaluate f of 0. Okay. To find x-intercepts. What's another name for x-intercepts? Zeros. What else? Zeros. Roots. Okay. To find these guys, what do? Set f of x equal to 0. That puts my y value at 0. That means I'm on the x-axis. Does that make sense to you guys? Okay. Now, I want to look at the problem that we just did. This guy right here. If I blow this function up, and I were to say, okay, let's find the x-intercepts. We're going to set this whole function equal to 0, and we're going to start solving there. Y'all see what I'm saying? My first move is going to be what? How do I get x by itself? It's a rational function. I've got it set equal to 0. What does your gut instinct tell you to do? It's the first thing you might do to get x by itself. Multiply. Me too. Multiply by the denominator. Multiply by the whole denominator. That whole x plus 3 squared times x minus 2. So that I can get rid of it on the left side. Are y'all seeing what we're saying here? Okay, if I do that on the other side, so 0 times x plus 3 squared times x minus 2. What happens when I multiply that whole denominator by 0? It makes 0. It cancels out, right? So actually, it doesn't matter what I do with the denominator. I don't have to set the denominator equal to 0. I only need the denominator portion when I'm finding discontinuities, domain, asymptotes, holes, that kind of thing. When I'm looking for x-intercepts, I only actually have to set the numerator equal to 0. Because in my algebra process, I'm going to cancel out the denominator anyway. Does that make sense? So really, if I wanted to find these x-intercepts, I would say x plus 1 squared times x minus 3 equals 0. And I would go find out where are my two zeros here. I've got 1 at x equals negative 1. That guy happens to bounce. I've got 1 at x equals 3. And you can see that those are right there on the graph. Are we understanding that? So in your notes on how to find the x-intercept, I think it's going to be really important not to say set f of x equal to 0, but set the numerator. Set the numerator equal to 0. No need to set the whole function because you're going to lose the denominator anyway. Yeah? Okay, so we're going to try example 10. And we're going to work this problem basically from the top to the bottom. And my hope for you guys is that after we do this one, we can do one more and then you're set. You can do your homework, you can do the test, you can do the whole deal. So we're going to do 2 examples and that's it. So example 10, it says graph f of x is equal to x minus 2 times x plus 3 over x minus 1 times x plus 2 times x minus 5. Everybody good here? Okay. And I want to graph it all over here, so I'm going to make a big graph. And then we're going to pull apart every single thing that this graph has to offer based on the function. First, we're going to start with our y-intercept. And I'm going to try to use different colors here so we can see exactly what's happening. So for the y-intercept, how do we find that? Plug 0 in for x, right? So we're going to evaluate f of 0. If I plug 0 into the top, I have 0 minus 2 times 0 plus 3 over 0 minus 1 times 0 plus 2 times 0 minus 5. On top, that's going to be a negative 2 times a 3. On bottom, negative 1 times 2 times negative 5. Okay, that makes a negative 6 over positive 10, or a negative 3/5. Is that what you said? Negative 3/5. If it was negative 3/6, that would be half. So we're a little more than halfway. I'm going to let this be negative 1. So my negative 3/5 is going to be just somewhere right in here. if my graph will let me do it. Right there. What do you think? Everybody okay so far? Now let's find our x-intercepts. How do we find our x-intercepts? Y'all are awake today. I'm loving this. Set the numerator equal to 0. So where are my two zeros? And do either one of them have multiplicity other than 1? No. So that means it's going to cross through on both places. X equals 2 and x equals -3. And both of them are like portals. Both of them are allowing the graph to go through. Okay. Now let's talk about the domain. Remember, the domain is going to be everything except where I would divide by 0 in the denominator. So x such that x is not equal to, in the denominator?
1, -2.
Good. 1, -2, and 5. And so it has to be the denominator because that's what would affect me dividing by 0. Right? So I cannot divide by 0. So I look at the denominator and I say, okay, where would I have to divide by 0? If x was 1, or x was -2, or x was +5. That's where I would be in trouble. Look for any holes. Do you see any holes? Any cancel buddies? No. Yesterday we learned that there are holes when I have common factors in the top and the bottom. If this little guy had been a +2, I might have had a hole there. But he's not. He's a -2. He's different. No cancel buddies. If there aren't any cancel buddies, then that means that I have vertical asymptotes in all three places. Vertical asymptote at x equals 1, x equals -2, x equals 5. That means it's broken in those places. So I write my vertical asymptotes with a vertical line dotted all the way through. And that's 1, 2, 3, 4, 5. There's another one over here. Yeah? There's one more piece of information we can put on this graph. This is called the horizontal asymptote. What's the rule on the horizontal asymptote? Right. So we're looking at the degrees of the numerator and the denominator. What's the degree of the numerator right now? If I multiplied these out, x times x, I would get x squared. And on bottom, if I played hippity-hoppity distributive property, I would end up with x cubed on the bottom. The rule is if the degree on the bottom is bigger, it goes to 0. If the degree on top is bigger, horizontal asymptote, there is none. If the degrees are the same number, top and bottom, so x squared and x squared, then you look at the ratio of leading coefficients, which in this case would be 1. But we don't have any because on the bottom, it's bigger. So that means that as we get to the end of the function, as x goes to infinity or negative infinity, the function's going to write out on that asymptote line. Cool? Okay. All right, so now let's plot what we have. When I start drawing this picture, based on all of this information that we just put on the boundary line, I always start in the region that contains the y-intercept. Okay? Because I know this thing's got to go through this dot right here, that y-intercept that we put, that little bitty blue dot. Okay, it should be almost to -1, this guy. Can you tell that there is no x-intercept in that region? My x-intercepts are green. So I don't have any in this region right here. What that means is that it's going to cross the y-axis, but it's not going to go up here. So in my mind, what that should look like is my two tails around that guy are going to have to go down. If they're not allowed to go up, then they must go down. Does that make sense? The only way it can get through the x-axis is through an x-intercept. It's like a gate, a portal. And this function's not allowed to go through the x-axis unless there is an x-intercept. And in this region, there's not one. And it's bound on the two sides by that vertical asymptote. It can't cross those either. So its only option really is to go up through the y-intercept and back down. Can you see what I'm saying here? Okay. Now, we come to the multiplicity of the asymptotes. All of the asymptotes have odd multiplicity. We didn't see any asymptotes that were squared in the bottom. Look back at the function. Any asymptotes are squared in the bottom? So what that means is that each one of these, our tails need to go in opposite directions. Okay? So in this first one, I've already got a down tail. So what does that mean about this one? It's got to go up. You seeing what I'm saying here? This has got to be an up tail because I already have a down tail on the other side. And it's going to cross through the x-axis right there through that green dot. And how does it behave as x goes to negative infinity? It should come back up toward the x-axis. I don't know if y'all are George Strait people or not, but I always sing that song, The Cowboy Rides Away. This is where the cowboy rides away. I'm thinking this cowboy's going off into the sunset, and as he's doing that, he's riding right along that x-axis. And he's got to ride it all the way to infinity. Does this make sense to you? Maybe I'm just weird. Okay. But that asymptote tells me that this function behaves toward that asymptote as it goes to infinity. It's got to come back and write it out. Cool? Okay, now let's get into this region right here. What happens? You've got a down tail, so you need an up tail. You need an up tail, and it's going to cross through the x-axis right there, and then it's going to go down as it gets toward the other asymptote. Got it? We've got one more little region to talk about. That's going to be over here. Is there an x-intercept over here? Mm-mm. So what we see is we've got an up tail because this one was a down tail on the other side. And as it gets to that asymptote, it's just going to write it out all the way to infinity. Is this the coolest thing ever? Hard no. I think this is the coolest thing ever. This is one of my favorite topics to cover. No. Bryson says no. Okay, fair. Let's go on to example 11. I did want to talk about one thing with you on this problem. Notice that I always have told you that an asymptote's a line we can't cross, right? And I've repeated that over and over. An asymptote, we don't cross asymptotes. We don't cross vertical asymptotes, ever. The graph is undefined on a vertical asymptote. But if you notice right here, this function crossed that horizontal asymptote. Can you see it? Okay. Well, how's it an asymptote if my graph is allowed to cross it? My function can go over the asymptote. How is that an asymptote? Horizontal asymptotes are about end behavior. They tell us what we do at infinity or at negative infinity. They don't determine what happens in the middle of the function. They determine what happens on the tails. Does that make sense to you guys? So it's allowed to cross up in here. It's allowed to have x-intercepts, and that doesn't affect it. What matters is that as we go to negative infinity, this guy's coming back up to that axis. Okay, that's what I'm talking to you about. That's like the cowboy in the sunset. He's got to go, as he rides off into the sunset, he's got to find that horizontal asymptote. Okay? I don't know if I trust that y'all guys understand what's happening right now. Okay, we're going to do a try it. This one's going to put together a whole lot of it. Are you excited? Yeah, she said. Okay. try it. We're going to graph f of x equals x plus 2 squared times x minus 2 divided by 2 times x minus 1 squared times x minus 3. Whoa. It's a lot of mamma jamba right here. This is going to be good. Raise your hand if you have a pulse. I'm not resuscitating. Don't get paid high enough to resuscitate. Okay, so I always start with intercepts. Always, I start with intercepts. And on your test, I'm pretty sure that's where we start. Okay. Your test, again, will only cover problems from this particular set. So I would say let's find our y-intercept first. How do we find the y-intercept? Plug in 0 for x. So we're looking at f of 0. If I plug 0 in first, I'm going to get a 2 squared times a negative 2 over a 2 times a negative 1 squared times a negative 3 not squared. Are y'all seeing where I got those numbers? Plugged in 0 for x. So the first 2 squared makes a 4, right? 4 times negative 2, negative 8. 2 times negative 1 squared. What's negative 1 squared? Negative 1 squared? 1. So 2 times 1? 2 times negative 3? Negative 6. So if I reduce that down, I'm going to have a 0 at 0, 4/3. 0, 4/3. So on my cute little graph over here, at 4/3, which is a little bit bigger than 1, I've got a y-intercept. Yeah? Everybody okay? Blink 2 times if you're awake. Okay. The next thing that I like to do before I start putting on a graph is find my x-intercepts. How do we find x-intercepts? Set the numerator equal to 0. So where are my zeros here? X equals negative 2 and x equals positive 2. Anybody notice anything else that's special? The x equals negative 2 has multiplicity of 2. What does that mean is going to happen on that x-intercept? It's going to bounce. It's going to bounce. So at negative 2, we got a dot, and at positive 2, we've got a dot. And I'm just making a mental note here that negative 2 one's going to have to bounce. Cool? Yes? Okay. Next, we want to talk about the domain. In this, we're looking at what? The numerator or the denominator? The denominator. We're looking for discontinuities. Our domain is going to be x such that x is not equal to, look in the denominator, 1 or 3. The 2 is not a problem. The 2 doesn't make me divide by 0. Okay. X not equal to 1 or 3. So I know there's discontinuities there in both of those places. Now check for holes. Look for any common factors. So no holes. You may have holes in your homework. Just heads up. No holes. Okay, what else? That means that we have vertical asymptotes. If there aren't holes, then there are vertical asymptotes at these 2 places. Vertical asymptotes at x equals 1. What kind at x equals 1? Look at its multiplicity. Can you tell that it got squared? in the denominator? So it's going to look like a volcano. Both tails are going to go the same way around it. And at x equals 3, they're going to go in opposite directions. It's regular. So go ahead and mark those two asymptotes on your picture. X equals 1 and x equals 3. And I know that at 1, I have that volcano action. We doing okay? One last thing to make note of. That's going to be the horizontal asymptote. Horizontal. Get it? Horizon. Oh, man. My George Strait's making more sense now. Horizontal asymptote. What's the rule? What do we look at? The degree of the numerator versus the degree of the denominator. In other words, the multiplicities of each zero. You can just add them up. What's the multiplicity of the top one? We got a 2 and a 1. So what's the degree? X cubed. And on bottom, same thing, x cubed. So now we go to the ratio of leading coefficients. That means the number in front of x. If I were to FOIL this out, what would be the number in front of my x term? If I had x plus 2 times x plus 2 times x minus 2, and I were to distribute all the way through, would there ever be a number in front of x? Not besides 1. There's going to be a 1. If I were to do the same thing on the bottom, would there ever be a number in front? What? 2. That's the leading coefficient. The number in front, the leading coefficient. So we go to the ratio of leading coefficients, which in this case is 1/2. So our horizontal asymptote is going to be at y equals 1/2. Yeah? So that means up here between 0 and 1 at y equals 1/2, there is a horizontal asymptote. Cool? Now we get to draw the picture. I always start with my y-intercept. My y-intercept is bound on the right side. This region is bound on the right side by this asymptote at x equals 1. It's bound over here. It's not bound to the left. Can you see that? So this guy is allowed to go to infinity as we sweep out this way. So what's going to happen is it's going to go through the y-axis and it's going to go up. This tail is going to come and ride that y or that vertical asymptote up. And I knew it was going to come up because as it goes out this way, it's going to ride that horizontal asymptote. Okay? But before it gets to that horizontal asymptote, what does it have to do? It has to go touch the x-intercept. Does it go through the x-axis? Why not? Because it's supposed to bounce right there. Notice that we wrote that. We said when it gets to x equals -2, it's going to bounce. So what it does is it goes down and it kind of kisses the x-axis and then it comes back up and it rides all the way off into the sunset. Now we have to draw what happens in the middle between the two asymptotes. And so we go and we look, and look what we wrote on the bottom. We have a volcano situation here. So what does that mean for the tail on the other side of the asymptote? It's got to go up. It's got to go up. And at the same time, it's got to go down through the x-axis. And then it's going to get alongside that other asymptote and ride it all the way to infinity. or negative infinity. Can you see it? And we've got one more region to talk about. Am I going to draw down in this area like this? Why not? Because this doesn't get to have an x-intercept. For one thing, I'm not going to be able to cross the x-axis somewhere up in here. For another thing, what kind of behavior do I have along this asymptote? How many multiplicities does that bottom asymptote have? Only one. So what do the tails do on it? Up and down, opposite directions. And we've already said this tail goes down. So the only one remaining has to go up. And then as we go out to infinity, what happens? Off into the sunset. On y equals 1/2. So again, your test will be on Wednesday, and it will cover problems from this only. Because in this particular lesson today, we've covered all of 5.6 Part 1 and all of 5.6 Part 2. And so we're only going to test on this stuff. You have homework assignment already. I'll post the solutions tomorrow. You've got a work day tomorrow, which is Friday. You've got another work day Monday. You've got a short class period on Tuesday, and we're going to test on Wednesday. Please, please, please practice. Use your time. Ask as many questions as you can possibly ask between now and when you take your test. Deal?